TM analysis of the rectangular metal waveguide. In this video, we'll go through the details of analyzing the TM mode of the rectangular metal waveguide. Given that solution, we'll look at that. We will learn it. We will analyze it. We'll then visualize the modes in this waveguide. We'll give an example, and that'll be it for this video. We'll conclude it. TM analysis.
Let's remember what happens for TM analysis. So TM means transverse magnetic. That means that the longitudinal component of the magnetic field has to be 0. So the magnetic field only has transverse components. Since that's 0, that means the differential equation that we're solving for is for the z component of E. So that's what we'll proceed with. And once we find an expression for E naught z, we can plug it into these equations to find all of the other field components, and then we would have obtained our solution. So that's what we're going to do. The general solution for the guide is the electric field is written as the product of two terms. The first is the amplitude profile. It's a picture of our mode in the cross-section of the waveguide. So it is only a function of x and y, and it does not change. The second term is the e to the minus j beta z. This is what's responsible for oscillation or accumulation of phase as our mode is propagating in the z direction. To solve this, we will again look at our rectangular waveguide as sort of the superposition of two parallel plate waveguides. So what we'll be doing is writing our solution as the product of two functions. One is only a function of x, so we'll just call that capital X. The other is only a function of y, and we will call that capital Y. And we can think of each of those, x and y, as a separate parallel plate waveguide. We'll analyze them as such, and once we get solutions, we will tie it together to get our overall solution for the rectangular waveguide. This is called the separation of variables. So we have our differential equation that we're going to solve. And we know that we're going to let our solution, E naught z, be the product of two one-dimensional functions. So the first step here is to plug in big X times big Y in place of E naught z. So when we do that, we end up here. And notice, just to be clear and compact, I'm dropping the parenthesis X and parenthesis Y, but make no mistake, big X is a function of only little x, and big Y is only a function of little y. I've just dropped it here. Now we're going to notice, since big Y is not a function of x, it can come to the outside of the partial derivative. Likewise, since big X is not a function of y, it can come to the outside of the partial derivative. So that's what we did here. Then last, I'm going to divide the entire equation by x and y. So I end up with a 1 over x multiplying this partial derivative and a 1 over y multiplying this. I said partial derivative. I actually meant ordinary derivative. They become ordinary derivatives because this big X is only a function of x. So our derivative becomes ordinary. Likewise, our big Y is only a function of y, so our partial derivatives become ordinary. So two things happen at once here. We divided the whole equation by x times y, and our partial derivatives became ordinary derivatives. So here's our new equation with x and y. Let's first think about the x dependence in this differential equation. Everything that depends on x is in this first group of terms. That means in terms of dependence on x, all of these other terms are a constant. So let's actually call that group of terms minus kx squared. And we chose to call it minus kx squared because our differential equation now becomes a one-dimensional wave equation that's easily solved. Next, we will look at the y dependence. All of the y dependent terms are concentrated here. Notice we've moved the minus kc squared term over here, and that's to group it with the x terms. So in terms of y dependence, all of these terms on the left here are a constant. So let's just call that minus ky squared. And why did I choose minus ky squared? That's so our differential equation becomes a one-dimensional wave equation, in this case in the y direction. So we have taken our single differential equation containing both x and y and have come up with two very simple one-dimensional differential equations. So we will solve these separately and then bring the solutions back together. Again, this is called separation of variables when we do this. So here's our two differential equations, and let's test to see if this is making sense. And the way we're going to do this is manipulate those equations, add them together, and see if we recover the original differential equation. So the first thing I'll do is divide the top equation by big X and the bottom equation by big Y. We end up with them in this form. Now we will add those together. At this point, we get a single differential equation, which was the sum of our two smaller differential equations. Let's compare that to the original differential equation. So in blue is the original differential equation, and we can see that these two equations will be the same thing if we let kc squared be equal to kx squared plus ky squared. So that will be our definition for the cutoff wave number, and it will let this separation of variables work for us. So we now have two different differential equations to solve. They're actually the same differential equations, so when we get a general solution from one, we can just copy that and write the general solution for the other. These are the same differential equations that we solved in the parallel plate waveguide, so we can just go ahead and write these immediately. The only difference here is our constants. So for our solution of x, we use a and b. I can't write just a and b for our solution of y because they're potentially different constants. So I write it as c and d. And they're the same solutions we got for parallel plate waveguides, and is really why it's kind of like we're analyzing a parallel plate along x, a parallel plate along y, and then bringing them together. So now that we have expressions for x and y, we can multiply them together to get the general solution for E naught z. So here it is, our general solution. We still have yet to find what a, b, c, and d are, and we do that by applying the boundary conditions. We have an easier job here because E naught z is already an electric field and tangential to our interfaces. So it's easier than the TE analysis. So here's our boundary conditions. We don't need E naught x or E naught y or anything else because E naught z is tangential to all of the interfaces. So we just apply the boundary conditions to it. Much simpler. Maybe we should have even done the TM analysis first.
We have the general solution and we have our boundary conditions. So we're now in a position where we're going to apply those boundary conditions to the general solution. And we have four boundaries, so we have four boundary conditions to apply. The first one we're going to do is at the x equals 0 boundary. So that's the far left-hand side of the waveguide. So the E naught z at the boundary all the way around on the waveguide has to equal 0. Here we're focusing just on the left boundary, the x equals 0. So this E naught z at x equals 0 must be 0. So we can go ahead and write the general solution and then plug in a 0 anywhere we had x. So what will happen then, this cosine term will just be cosine of 0. So that will be a 1, and we're just left with the a constant. But sine of 0 goes to 0, and this b sine term vanishes. So we can go ahead and eliminate that. And here's our revised general solution. Now this must be 0. Looking at all of what's going inside this second set of square brackets, well, nothing in here can make this go 0. So we have to have a equals 0 in order for this to always be 0. So that's our first answer, that constant a is 0. Now we can look at the far right-hand boundary. That's at x equals a. So just like above, we're going to do the same thing. We'll write the general solution, but we're going to put in a value of a for x. And here we are. Notice we've already eliminated the a term because we know that a is 0. So we just have the b sign term. Well, this whole thing has to equal 0. And what's going on in the right set of square brackets, we can't do anything there to get us to 0. So it must be something in these left brackets. And well, there's one of two things we could do. First, we could set b equal to 0. Well, if b is equal to 0, then this whole solution will just always be 0. So that's not an option for us. Something else has to give. And it'll turn out it's this sign term that has to go to 0. Well, let's set sine of kxa equals to 0. And the way we do that is if this kxa is some integer multiple of pi, right? Because the sine function of integer multiples of pi is always 0. Now, looking ahead a little bit, it will turn out that we can't choose m equals 0. At this point, we could, but later on, we'll show that this leads to a trivial solution. Let's repeat everything we just did, but for the y-axis boundaries. So the first boundary is at y equals 0. So this is the very bottom of the waveguide as we've defined it. So E naught z at a value of 0 for y has to equal 0. So hopefully you get the pattern now. We're going to write out the general solution and plug in 0 for y and figure out what the constants need to be in order to get this whole thing equal to 0. So we write the general solution, and notice I'm still keeping a. I'm just showing that no matter what we do over here, the conclusions we're about to draw are just derived from these right square brackets. So we put in a value of 0 for the value of y. And cosine of 0 is a 1, so we'll just have the c coefficient. And a sine of 0 is 0, and so this whole d times sine vanishes. So we'll get rid of that. And we just have this c coefficient. Now, this whole thing has to equal 0. Well, this stuff in the left set of square brackets can't help us get to 0. So it must be c that equals 0. So we found that the constant c equals 0. Now we go to the fourth boundary. This is at the top of the waveguide, or y equals b. And we're going to repeat the same procedure where we write the general solution, but we'll put a value of b in for y. And so the electric field at the top of the waveguide has to be 0. So we write the general solution. We've dropped this c cosine term because we found out c is always equal to 0. So it's just d times sine kyb. Well, we need this entire thing to be equal to 0. We've already said the stuff in this left set of square brackets can't get us to 0. It has to be the d or the sine. And if we set d equals 0, that's going to give us a trivial solution, and we only ever see the 0 solution. So it has to be this sine term that is getting us to 0. So we set that sine term to 0. Well, how do we get a sine function to equal 0? When its argument is an integer multiple of pi. So that's exactly what happens. When this kyb is an integer multiple of pi, we'll get an answer. That sine goes to 0. Now, I'm not using m as I did for our x-axis boundaries. I'm using n because this is a sort of a different problem. It's a different set of boundary conditions, and it will turn out we will be retaining m from the x-axis boundaries and now this n from the y-axis boundaries. And looking ahead a little bit, the n equals 0 will be a trivial solution and won't be valid for us.
Now that we've applied the boundary conditions, let's bring all of this together again. We found through the boundary conditions that big A and big C have to equal 0. So our expression for E naught Z reduces to this. And we have this B times D. We weren't able to find values of B times D. Since B times D, they're both unknown constants, their product is still another unknown constant. So we'll just call that B sub mn. And B sub mn will be the amplitude of our mn order mode. Remember what we found for kx and ky when we applied the boundary conditions. Kx was m pi over a, and ky was n pi over b, so we can write our field solution this way, eliminating kx and ky. Remember that neither m nor n can be 0. So if any mode number has a 0 in it, we can't have that one. That's not valid for the TM modes. So we take this expression, we plug it into our equations for calculating all of the other field components, and we end up here. And of course, the very last thing to do is to tack on this e to the minus j beta z term. And I've included an mn subscript on our beta, and that's indicating that each of the guided modes has its own phase constant, also has its own amplitude term.
Analysis of the TM solution.
Let's think more about the phase constant. Remember our separation of variables, how we were required to define the cutoff wave number as the sum of kx squared plus ky squared. So we found expressions for kx and ky that enforce the boundary conditions. So now we have an expression for our cutoff wave number just in terms of m, n, a, and b. Originally, our definition of this cutoff wave number was k squared minus beta squared. We can solve this for beta squared, which is now k squared minus kc squared. We have an expression for kc squared that we can plug in down here and solve for our phase constant just in terms of k, m, n, a, and b. So clearly, since m and n are in this equation, the phase constant will be different for each of our modes. Now let's think about the cutoff frequencies. So we have this general equation for beta, and in order for it to be a guided mode, the argument inside the square root has to be positive. So that means that k has to be greater than kc in order to keep that argument positive. That's why we call kc the cutoff wave number, and that's because it defines where cutoff happens. From that, we can figure out the cutoff frequency. So knowing that k has to be greater than kc, we know that k is omega times the square root of mu epsilon. Omega is our angular frequency, so that is 2 pi times the ordinary frequency being the thing that's in hertz. So we solve this for our ordinary frequency, and we can calculate the cutoff of the mn mode. And recall, that's the same equation that we had for the cutoff of our TE modes. So the equation for the cutoff frequencies is the same for TE and TM modes. That's handy because we can calculate both at the same time. The characteristic impedance for the TM modes, it's the amplitude of E over the amplitude of H. So we can plug in our expressions for E and H and simplify, and we have our final expression for calculating the characteristic impedance. And our phase constant now is known because we've done the wave analysis. Let's look at cutoff frequencies. So what is the first order mode for the TM modes? So here's our expression for the cutoff frequencies, but which one is the lowest order mode? So remember, neither m nor n can be 0. So TM00 mode can't exist. TM01 can't exist. TM10. TM anything with a 0 anywhere does not exist. So we cannot consider those. So what combination of m and n does minimize FC? Let's give this a bit more thought. So it turns out the TM11 is going to have the lowest cutoff frequency. And so if we plug in 1 for both m and n, here's our expression for the cutoff frequency for the TM modes. Now, we can't say that's totally the fundamental cutoff frequency for this waveguide, because that's only the cutoff frequency for the TM modes. We would have to look at the TE modes and figure out which of those two actually has the lowest cutoff frequency to figure out which is the fundamental mode.
Visualization of the TM modes. It makes sense the first mode we look at is the TM11, since that is the lowest order TM mode. And here we're looking at this cross-sectional picture, just the Z component of the electric field. So keep in mind, you're not seeing everything. This is just the visualization of the Z component. Visualizing the vector-guided mode is a bit more complicated. But we can interpret the subscripts, again, as the number of bright spots along each direction. And we see one bright spot along X and one bright spot along Y. So we can immediately recognize visually it's a 1-1 mode. And of course, since we're looking at EZ here, that would be the TM11 mode. But this picture does not change. It appears to change because we see red, blue, and they're moving, but it's just this same picture accumulating phase, but inside the waveguide, we're just looking at the real part. Well, the next mode would be T12. Let's interpret this as the number of bright spots. So we have one bright spot along the x-axis, so that first subscript 1 makes sense, and then two bright spots vertically. And we see two bright spots, and we also see they're different colors, meaning they're 180 degrees out of phase. Now, all of this is even more apparent if we're just looking immediately at this cross-sectional picture. Again, this cross-sectional picture does not change. All it does is accumulate phase as it propagates down the waveguide. TM21. Now we should see two bright spots along the x direction and one along the y direction. So if we look at the x direction, yes, we definitely see two bright spots and they're 180 degrees out of phase. And in the y direction, only one bright spot. TM22, we should see two bright spots along each axis. And we definitely do. Two bright spots along x, two bright spots along y, and along each of those axes, they're 180 degrees out of phase. So one's red, one's blue, and one's green. Back to visualizing the TM11 mode. This is a little bit of a different type of visualization. Here we're looking at the vector cross-section, the X and Y components of this guided mode. So on the top, we see this picture. And on the bottom, we see the picture, but we're also looking at, on the white arrows here, the vector nature of the field. So we're not looking at the Z component here, just the X and Y components. But a true guided mode, it's going to have X, Y, and Z components. And it's really, really tough to show all of that at the same time. Example.
So here's an example. And we're going to go with the same rectangular waveguide that has a width of 3 centimeters and a height of 2 centimeters. What is the cutoff frequency of the waveguide? Well, we know that's when M and N are 1, so we plug in all our numbers, we get an answer of 9 gigahertz. And I'll remind you again, this is really just the cutoff frequency of the TM modes. The overall absolute cutoff frequency of the waveguide, we'd have to also consider the TE modes. But we're just looking at the TM modes right now. And the TM11, which is the lowest order mode, has a cutoff of 9 gigahertz. So as far as TM modes are concerned, below 9 gigahertz, this is a useless waveguide. Like before, let's plot the phase constant and the effective refractive index. And we're seeing similar things. Below the cutoff frequency, we don't even have a phase constant. It doesn't exist. It's actually imaginary. But right at 9 gigahertz, suddenly we have this phase constant. And the effective refractive index looks very similar. Notice it's also always less than 1. So our TM modes also appear to be traveling faster than the speed of light. I'll say it again. Does that bother anybody? So if we take the speed of light divided by our effective refractive index, we can actually plot the velocity. And we can see that below the cutoff, it doesn't even make sense to talk about that velocity. But right at cutoff, the velocity approaches infinity, and it falls pretty quickly, but it hovers between 1 and 2 for a while, eventually way out here at super high frequencies converging to just 1. But for the most part, where we're using this, that velocity is greater than 1, and it's faster than the speed of light. I hope that's bothering you.
Conclusion.
So here's a summary of what we've done. On the left is all of the fields for the TM modes. We have a way of calculating our phase constants, our cutoff frequencies, and characteristic impedance. The equations for phase constant and cutoff frequency, they're the same as the TE modes. In terms of ordering the modes, M and N, neither of those can be 0. So any mode number that has a 0 in it for TM is not a supported mode. And we found that the TM11 is the lowest order TM mode. We can't say that's the absolute lowest order mode because we have not checked the TE modes.
From the bottom of my heart, thank you so much for using EMPossible. I want to create more videos, and I want to continue to improve how electromagnetics and computation is taught online. To do that, it will really help me if you can like this video and subscribe to our channel. I also want you to know we have a lot more content that you may not be aware of. See everything we have to offer at EMPossible.net.